Welcome friends, we are in Unit 3. We're going to cover Lesson 11 and 12 today because this is more of a continuation about that number I that we talked about yesterday and what we can do with I once we know that it is out there and it does exist, even if we have to use our imagination to make it exist. So just a quick reminder that yesterday we learned that I is the same as the square root of a -1. And today we're going to start putting some of that into action. All right, so when we need to find a value of each expression, we start here just thinking about first numbers and then how that's going to also start applying to this I number that we are just introduced with. Remember, if something is squared in parentheses like this, it does mean that it goes to both of those objects inside the parentheses. So if we had something like 2 square root 3 squared, it is 2 squared and the square root of 3 squared. And maybe you're saying to yourself, well, we can find values for both of those. 2 squared equals 4, and square root of 3 squared are going to cancel each other out. We would have 4 times 3, which equals 12. And applying the same to our next problem, we would of course have 1/2 squared and square root of 3 squared. Well, half squared means 1/2 times 1/2, which multiplying fractions straight across, 1 times 1 is 1, 2 times 2 is 4, so that would equal 1/4. And of course, square root of 3 squared is still times 3. So we have 1/4 times 3, which would be 3/4. Now we can always check this on a calculator. Sometimes it's a good idea just to give that a try. Right? So 0.5, let me hit clear because I want to use those parentheses, same thing that my problem is given to me in. 1/2 the square root of 3. And I need to square that, and it tells me, oh, I see what I did, sorry. There we go, that makes more sense. Sorry, my error of how long my radical was going across made that an incorrect answer. I have to follow my own rules of being careful that what's inside the parentheses matches what we start inside the parentheses. So 1/2 times the square root of 3, parentheses squared, does equal 3/4, 0.75. We already know that 2 squared equals 4, so we have a 2 squared here, and that's square root of -1 squared. 2 squared equals 4. And this is interesting. The square root of -1, which we know as I, of course, square root of -1 equals I. Now we're finding out that I squared cancels out, and we're still left with -1. So that's an interesting little fact there. In fact, it's so interesting, and we're going to need it pretty frequently, that I'm going to also add that up here in my lesson 11 intro thing, that I squared equals -1 because squareds and square roots are opposite each other. Okay, good thing to know. I'm going to keep that in mind. And again, 1/2 squared, we already calculated that up here, so I'm just going to write that as 1/4. And square root of -1 squared, I squared, equals a -1. Multiplying those together, we get -1/4. So some pretty neat stuff going on. Big idea here. And we can start to see that the same policies of square roots even work with negative numbers, even work with I. So when we start looking at some solutions to these equations, we're going to plot them here and remember again that we have a real axis here and an imaginary axis here. And so if I have the a squared equals 16, well, I can think about the square roots of 16. Square root of a positive number, it's a very real number that we have. We can think again about that parabola and equaling 16 in two places. A would have to equal 4, and A could also equal negative 4, starting with a squared, two possible solutions. So 4 and negative 4 is where we would plot those answers. When we start doing something like taking the square root of negative 9, there's that square root of a negative going on. My rules actually tell me that I can make that the square root of negative 1 and the square root of 9. Multiplying two separate radicals like this together still has the same value. It's like I can take it like this, negative 1 times 9, and break it up into two parts. I do that because I think that radical here, that square root of negative 1, is I, and the square root of 9 could be 3, or it could be negative 3. So this is how we're getting 3i and negative 3i. And we just usually put like that coefficient in front, just like we would in front of x. When we were writing coefficients with x, we very rarely see something like x3. We would instead say 3x. So we usually keep that coefficient in front, just like with variables. So 3i and negative 3i plotted. And c squared equals negative 5, square root both sides. We know we're going to get a positive answer and a negative answer. We know there's a square root of a negative, so we could pull that out as an I, because we could break that up as square root negative 1, square root 5. Now square root 5, I can't find an exact value, so maybe I just want to have it like that, where I have a positive, negative, square root 5i, clearly stopping the square root, so I'm not taking a square root of I. So either one of these would make sense. Now I have to kind of estimate what the square root of 5 is, so I can now plot that. It's obviously more than 4, because, 2, because 2 squared is 4. I need a little bit more than that. So it's a little bit more than 2 and negative 2. So we can see that we can find some values of I going on here, and how we can graph those. When the i's have it, just like we did before previously, we want to break it up into some maybe more familiar ideas. So if I can break this up into the square root of 36 times the square root of negative 1, that's a multiply there. Well, the square root of 36, remember now I'm given a square root in the problem, I'm not given squared. Square root of 36 is the positive 6, because I need only the positive radical. Square root of negative 1 is I. Square root of negative 10, we can break that into the square root of 10, the square root of negative 1 multiplied together. Square root of 10i, or some people like to still write that as I square root 10 to make it clear that the I is not underneath the radical. Either way you go, you're good to go. I'm not going to gig you if you have it one way and not the other. Now this one does have the negative sign in front, so I need to make sure I keep my answer as a negative. Square root of 100, square root of negative 1. Maybe your brain is already starting to speed this up to find negative 10i. And last but not least, again with a negative in front, negative solution, I root 17, because that's not an exact number, or negative root 17i. So we can rewrite these numbers using I, noticing that we're starting with positive or negative radicals and sticking with our same rule, that If it's a positive radical, we'll have a positive answer, a negative radical, a negative answer. Now, 11.4 just asks you to label 8 different imaginary numbers on the imaginary number line. I don't know. Look, there's I. Look, there's 2I, and 3I, and 4I, and 5I. Negative 1I, and negative 2I. Just reinforcing that we have our real numbers if we're using these planes and our imaginary numbers. Oh, but complex numbers. So we can label imaginary numbers here like 4I and 5I and negative 4I. But complex numbers, actually, we can have them anywhere on this grid. Just like our x and y's, we aren't stuck with just x values and y values. We can have x, y ordered pair coordinates. Complex numbers can do the same kind of thing too. So if I have something like a point, say, out here, just like an x and a y coordinate, we would have our x kind of part first. We're going to have our real part first. We have 4, but we also have a 2i component. So we have a real part and an imaginary part. In fact, that's what a complex number is. It's a real part with an imaginary part that represents something that combines the best of both. So a complex number is in the form a plus bi. You're going to see that a couple times throughout our unit, where the a is the real part. We start with our feet in the real world, and then we're going to dip our toe into imaginary. So we start that here. A real part with an imaginary part. Maybe you're thinking, well, what about something like this? And we see the real part is a negative 2, and the imaginary part adds 5i. So, complex numbers blend a little real and a little imaginary together, and that's what makes it so complex. Our last section in lesson 4 is talking about adding complex numbers together. So, here it is. When we add a real number and an imaginary number, we get a complex number. Add a real and an imaginary equals a complex. Pretty awesome. Our diagram shows 2 plus 1i in the complex number plane. And so we can start having our other points here represented by point A. If I had to find out point A, well, I have to go negative 4 on the real number line part. And then I have to go up. Let's see, here's 1i, 2i, 3 i's. So I'm going 3 positive i's. So A would be negative 4 plus 3i. It asks us to plot all kinds of points down here and to label them, so we'll just keep on following that same kind of practice. If I needed to plot negative 2 minus 1i, I would be down here in quadrant 3. This is point A. I'm doing it in blue. And I'm going to do part B in green. Negative 6, so I'm starting here, going over to negative 6. And now I need to go to positive 3i. 1, 2, 3. There is point B in green. Point C in red. Start at that origin. 5 real parts of it. 4 imaginary parts. 2, 3, 4. Put your point there. Label it. Point C. And last but not least, I'm going to do that last one here in black. Positive 1, negative 3i. So we can see how graphing is going to make this happen. And then what that does is leads us really, really nicely into continuing into lesson 12. So now that we know what a complex number is, nice reminder here with our summary, let's take a look at lesson 12 and see what we can start now doing with these complex numbers. Now we mentioned how we can use imaginary numbers to help us describe things like electricity and also space travel, big stuff, how light travels, how space travels. They will have lots of complex parts to them. We're going to have real parts and imaginary parts because electricity has a very real component to it. It can really, really shock you and might actually kill you. It turns on lights. It makes motors run. There are so many things that electricity does in the real world. But also it's got an imaginary component to it. We sometimes have to think about that. And it's this arithmetic that we can start to do with complex numbers. We talked before about having some kind of a battery and how if you hook things up a certain way with a battery, it'll do certain things. But we can also hook it up in what's called series. So maybe I'm going to turn on a light bulb, and then it's going to continue on with another wire, and it's going to power another light bulb. Maybe you're thinking strings of Christmas lights where you can plug them in end to end. And maybe then I'm going to have it power a radio. There's my speaker. I don't know how to do a radio. There's some dials and stuff. And then it's going to continue back in here. So I need to know all of these things, and I have to be able to figure out how much electricity is being used for the light bulb, plus how for my second light bulb, plus for my radio, and be able to hook that up. So we're going to need to be able to do arithmetic with complex numbers. We're going to start with our basic addition and subtraction. This math talk just gets you thinking about these mentally. I'm going to show you how I do it. I always think if I have a positive 2 and a negative 2, whoop, that's 0. Positive 20, negative 20, and positive 200, negative 200 equals 0. And it doesn't matter if they put them in a different order. Positive 10 and a negative 10 is still going to be 0. Negative 50 and a positive 50 is still 0. And a positive 100 and a negative 100 still would equal 0. 1, 2, and 3, if I add those is 6. Minus 1, 2, and 3 is a minus 6. So I'm kind of getting to this idea that we can start to balance things off and we can add and subtract in any order. 16s, 8s, plus 4, minus 2, plus 2. We're still left with this 32 in the middle. So they're just getting you back to thinking with arithmetic and how it works in any order. Adding complex numbers kind of does that same idea. Now we've got two complex numbers going on here. And so we're going to start looking through how we can add complex numbers and then how we can do it without a diagram. That's what's coming up next. So to see our first number of 2 plus 3i represented, it starts at the origin, it goes over 2 real, it goes up 3i, and it stops here where that arrow is happening right there. So I see it by origin, over to the right 2 units, and then up 3 imaginary units. And now if I'm adding negative 8 minus 8i, I see that happening here. That negative 8, it's starting from that end point and it's subtracting 8. 1, 2, 3, 4, 5, 6, 7, 8. So I see it from the end point. from the endpoint of 2 plus 3i. It moves 8 in the negative direction, so we go moving 8 units left. And then 8 imaginary units, that means down. And it looks like when we add those things together, we arrive at a final answer, a final point here of 8. So that complex answer represents, let's see, it's negative 6. And it's going down to negative 1, 2, 3, 4, 5. Negative 5i. So if I did the same thing, just by adding the like terms in the expression, go back to that Algebra 1 where they might have had you circle the like terms, 2 plus negative 8, and our other like terms, 3i plus a negative 8i. Ooh, we got the same answer. So we can add things using a grid. We can add things just by combining like terms. Combine the real parts, combine the imaginary parts. Let's see, we're going to take care of that here, and then we're going to stop after that. The 12.3 section we're going to skip for here because multiplying on a complex plane starts to get a little interesting. It asks for the sums and differences, so we can add or we can subtract complex numbers. Okay, and it says to check your work by drawing a diagram. We're going to try it a different way. So, adding the like numbers, we can even stack these up. Negative 3 plus 2i plus 4 minus 5i. Negative 3 plus 4 results in 1 positive. 2 positive i's, and I take 5 away is going to leave me with 3 negative i's. So in a mathematical sense, if I had some kind of a resistance or capacitor that could handle negative 3 plus 2i, and I put another one in series that is 4 minus 5i, my ending result would be a 1 minus 3i. I'm going to keep on doing those same things, maybe in a different way here. Negative 37 plus 11. Negative 26. Minus 45i plus 81i. Let's see, 80 minus 40 would be 41. I need to subtract another 5. So 41 minus 5 is 36. So my answer is negative 26 plus 36i. Now if we have our calculator set to the right setting, and I think we might have done this before, most of our graphing calculators can use imaginary numbers. Very few pocket calculators have imaginary numbers on them. So if you go to mode first, we always want to check that we are in A plus BI form. Now you know what that means. We have a chance that we usually have it set in real mode, and that means we can only have real numbers and real answers. But if we select this, and I'm just changing it by hitting the enter button so that A plus BI is highlighted, I see that I'm in imaginary mode. And that means I can have imaginary inputs and outputs as well as complex inputs and outputs. Now we're just going to be able to use this to check because we may not have a calculator when it comes time for a quiz or a test. And adding and subtracting like terms like this is not too tough of a deal. So, negative 37 minus 45, and the I button is here at the shift decimal. Okay, So it's right above the decimal. You see it right there with the I. So you need to hit second decimal. Second first, and then the decimal. And your calculator should put an I there. And we want to close those parentheses and add 11 plus 81I. And we can see we're getting a nice match. Now I'm going to do everything else by hand because I'm pretty confident in my addition and subtraction abilities. But remember, subtraction applies to everything here. So you may want to do something like rewrite this like negative 3 plus 2I. And then apply that minus sign. So draw your line, change your signs. Or maybe you just like to stack it up and keep on remembering that you are doing subtraction. No, that's a minus. Sorry about that. Negative 3 minus 4 more, or negative 3 plus negative 4 is a negative 7. 2I plus 5I, or 2I minus negative builds a positive. Negative 7 plus 7I. Or taking those real parts and subtracting negative 37 minus 11 more is negative 48. Negative 45I minus positive 81, but that's really more subtraction going on. Negative 45 minus 81 more is negative 126. So we have a negative 48 minus 126I. Now we can start to multiply on the complex plane, especially when we understand something that we talked about in the warm-up. I guess I will take a quick look at this because we've got a little bit of time. Graphing 2 here on the real number line is there. 2 squared we know is 2 chunks of 2, or 2 times 2, which is 4. I'm doing that in black. Now taking 4 and multiplying it again by another 2. 2 to the third power is 8. And 2 to the fourth power means I'm taking 8 and multiplying it by another 2. I need to be up here at 16. So you can see that it starts to get farther and farther away as we go. Same thing, well, something different starts happening when we use complex numbers. 2I, this is an interesting place for them to put this. Okay, so writing them in the form A plus BI is so interesting because there's no real part for any of these. So it's just saying that there's no real part and there is an imaginary part. So 2I is 0 plus 2I. And then to plot that on the complex plane, I'm going to keep my green pen. 2I is right here on the complex plane. 2I squared. 2 squared is 4, and then I squared, if you remember in our warm-up, I squared equaled a negative 1. That's because we took the square root of negative 1 and we squared it. I is the square root of negative 1. So square root of negative 1 squared is negative 1. So 4 times I squared, 4 times negative 1 gives us a negative 4. Now that's a very real number. Notice that when we square that, that became a real number. It's a negative number, but it's a very real number. So there is no imaginary part to that. So 2I squared, I'm going to do it here in red, so I just circled it so that I know I'm doing it in red, is here at negative 4. That's really our 2I squared. Now 2I to the third, I'm going to do that here in purple. First of all, I need 2 to the third, and then I need to figure out what I to the third is. 2 to the third is 8. I to the third, I'm going to come over here and I'm just going to write down what I to the third is, because I to the third is I squared times another I. Well, I squared is a -1. I is just I, so I to the third actually equals -I. Now there's interesting. So I actually back up here have an 8 times a -I, which equals a -8I. No real part, all imaginary. That's really an interesting idea. Oops, sorry, didn't show you where I graphed that. There's that -8I. So these are getting like farther away, kind of in this like weird spiral going around outside. If I anticipate what I think might happen, I'm going to guess that maybe our next one is going to be over here if these are really working in this kind of spiral idea. Let's see for sure. Picking up a different color. 2I to the fourth. 2 to the fourth equals 16. I to the fourth. Now I'm going to come over here and figure out what I to the fourth is now. I to the fourth, hopefully you're seeing that I to the fourth, I'm going to break it down into I squared times I squared. I squared is -1, and a -1 times a -1 is a +1. So I now have 16 times 1, which is just 16. Again, a very real number, no imaginary part. I think that's the end of our lesson, yeah. So some other reviews and stuff like that, but we're going to continue this idea in a later lesson that I equals square root of -1, I squared equals -1, I to the third is -I, and I to the fourth is a +1. Here's a neat way to see that here in action. Use any remaining time, if you would, to work on your practice problems for lessons 11 and 12. Thanks.